Let's have a look at bond polarity and molecular polarity. We're going to use electronegativity to determine where in a molecule atom or electrons spend their time. So you may want to pause this and have a look at these definitions, but the differences between a polar bond, a polar molecule, and a dipole. So here's a look at HCl. Where in HCl are the electrons from that hydrogen-chlorine bond drawn? That density map there shows that they seem to be drawn towards chlorine. I'm going to use a simulator from PhET and the HF molecule to examine this. So here's HF. If I have a look at this electron density function, this tells me that the electrons in the HF molecule spend their time around fluorine. Well, how do you figure this out if there isn't a simulator handy? Alright, use the electronegativity values. So, hydrogen and fluorine's electronegativity values are 2.1 and 4.0 respectively. Alright, I subtract them, and I see the difference is 1.9. So this is a highly polarized molecule. I represent that by drawing an arrow from hydrogen to fluorine, and I put these symbols, delta positive and delta negative, in, showing that the electrons are drawn towards fluorine. I can put a yellow arrow using the simulator showing that the overall molecule has polarity that's located towards the fluorine. Let's look at N2. So this is nitrogen. Nitrogen has two highly electronegative nitrogen atoms in it. So both of them have a value of 3.0, but when you subtract 3 from 3, you get 0. So this means that the electrons in that bond aren't drawn to either nitrogen more so than the other. When I click on the molecular dipole, so the yellow arrow, there is no yellow arrow. Alright, this density map shows that electrons are evenly spaced between the two nitrogens. This is what we would refer to as a nonpolar bond and a nonpolar molecule. Let's have a look at something else. How about carbon dioxide? Carbon dioxide has two very polar bonds, so you'll subtract oxygen from carbon from oxygen, so each of the bonds has an electronegativity difference of 1, so I would draw arrows indicating that both the oxygens are what we would say delta negative and that carbon is delta positive. But look what happens when I turn on the molecular dipole. The two carbon-oxygen bonds basically cancel each other out. So the molecule itself is considered nonpolar. Alright, you can see from the density map that it's essentially symmetrical. Alright, so when we say a molecule is nonpolar, we're saying that the electrons are equally shared around the molecule. Alright, so let's have a look at something else. Alright, if I were you, I would try to draw the Lewis structures for each of the molecules and see what you can come up with. So, water. Alright, here's the electronegativity values. I can do the subtraction there, and then I'm going to turn on some polarity arrows. Alright, the polarities don't cancel. This is a polar molecule. Alright, try CH4, methane. Alright, 4 carbon-hydrogen bonds. There's a little bit of pull in each direction, but nothing substantial. Alright, all cancel out, nonpolar. Have a look at CH3F. Alright, highly polarized bonds, especially between carbon and fluorine. Alright, but I can just look at this and I can say it's not a symmetrical molecule. Alright, and it would be polar. Have a look at the simulator for yourselves here at this site. Try a few of them, and we're going to go back through your Lewis structures that you drew last week in class, and we're going to try to assign the polarity of each of those compounds tomorrow. That'd be Monday in class.